Start it again. Okay, now we started, I think, one of the days ago, last week, of dealing with connections between propositions, where we looked at the connection of conjunction, where P and Q are true only if both P is true and Q is true. And we noted that that's what's going on with a linear system, in which we have a linear system. The fact that it's a system is related to the fact that both of the equations have to be true in order to find a solution. So we have to, a solution is going to say solve one of these systems, say this 3-equation system, only if it makes this true. That means it satisfies at the same time all 3 of the equations. Okay, and I think we didn't quite get to one of the more difficult logical connectives, so I wanted to take a moment and do that. That's the idea of the guarantee. It's also called implication. It's often translated by if P, then Q. So you'd say, okay, if it is snowing, then it is cold. The problem is that with using if then in English is that oftentimes if then is used for many different purposes. For example, here we know there's a physical connection between being cold and snow. So you tend to think of this as somehow meeting some logic, some kind of physical or semantic connection between this first piece called the condition and the second piece called the consequence. Okay, so what does this mean? Well, it's like I know that P and Q, there's many different possibilities. They could both be true. One could be false and the other true, or they could both be false. Those are 4 different scenarios or situations, and this other proposition is completely determined by these truth values and this truth table. So this is how we're defining P implies Q. Well, it's true here, it's false here, it's true here, and it's true here. Now, these first 2 sort of make sense. I mean, if the way I want you to think of this semantically is the truth of P guarantees the truth of Q. So if P, this says, okay, if P is true, then if this is true, it's got to be that Q is true. So this sort of makes sense. And this one also makes sense in the sense that, okay, if P is true and Q is false, then P wasn't a good guarantee. So this isn't a good guarantee, so it's false. But these 2 are sort of unusual. We need to have some value here. And you may want to put a false here, but the idea here is, well, if the condition isn't true, sort of all bets are off. We didn't really bring the guarantee into play, so we're going to say it's true. This is a notion called material implication that is it has a number of counterintuitive consequences. And you may sort of remember this, but then you can also sort of make this specific. For example, let's say we have this proposition 2 plus 2 equals 5. Right arrow. Let's see, what can we say here? We could say we are all millionaires. Okay, now is this statement true or false? What do you think? So I want you to choose a value. Think about this and choose a value for this claim here, that if 2 plus 2 equals 5, then we are all millionaires. Is that true or false? And then I'll tell you what I think. So raise your Zoom hand when you're finished with this. Okay. Okay, so the way you analyze, this is just a special case of when it thinks, well, this is false, and we don't know. This could be true or false. Okay, it's unlikely. I mean, that we're millionaires. Probably you might not be here if you were a millionaire. Or maybe you would be. Okay, but the point is that means you're in the bottom two rows, so this is true. So it's true according to this notion of if then, that if 2 + 2 = 5, we're all millionaires. Now, the reason that sounds weird is because there's no semantic or causal connection between this math fact and something in the real world. I can put any proposition I hear I want, and this is still going to be true, because the only way this can be false is if this is true. So if on Rig X or some exercise where I give you specific propositions, and what you want to do is you want to just figure out, okay, is the condition false or true or false? Is this true or false? And then you look at this table and figure out which row you're in, and then mark the answer accordingly. So when I give you specific things in the exercise, it's just a question of this table. This is just all that's going on. Shruti.
Why is the implication true?
Excuse me?
Why is the implication true?
Why is this implication true?
Yeah.
Well, this is false,
Yeah.
right? This is we don't know. This can be true or false, right? I mean, I'm not a millionaire, so we know that this is false. Okay.
But I guess
So that means we're in the bottom row here. False, false. So this implication is true by definition of what we mean by if then. Now I can make this plausible by sort of making a scenario in which this makes sense. For example, if you bought a microwave from a company, and they gave you a guarantee that if you did in the first year, if you didn't open the back where there's a seal, they'll fix it for free if it breaks. So then you could say, well, if it breaks and you haven't opened the seal, then we'll fix it for free. Well, let's say that you can go through each one and say, okay, well, if it's true that it broke and you haven't done the seal and they fix it for free, you can say, yeah, the guarantee was a good guarantee. On the other hand, if it broke and during the first year and you didn't break the seal, but they refused to fix it, well, you would say, well, you lied. Your guarantee wasn't good too. What you said was false. You said you'd fix it for free and you didn't do it. Okay, well, what about this? What happens if it broke and you opened it up and broke the seal? So that means this premise is false. Well, you could go to them and say, well, we're not going to fix it for free because you broke the seal. Our guarantee was still a good deal. If you had not broken the seal, we would have fixed it. So their guarantee is still a good guarantee. On the other hand, they might be generous and say, well, you broke it, but we see that you didn't do anything, so we'll fix it for free anyway. But no matter what, whether they fix it or not, their guarantee is a good guarantee. In the second case, they were just generous. So that's a case in which it sort of makes sense, these values, in answering the question. So this idea is the truth of P guarantees the truth of Q. But if P is not true, then the guarantee was still a good guarantee. You just didn't fulfill the conditions in the second, third, and fourth rows. Does that?
Yeah, that makes sense.
Okay, you have a different.
Yeah, so in that case, then I was just saying year old millionaires. How would we determine whether the implication is true or false if year old millionaires could either be true or false?
If the what?
If year old millionaires could either be true or false.
Right, P could be true or false, so you don't know.
Q could be true or false.
Okay, yes. The point is you have to make this work, you have to be able to determine whether or not this is true or false. Because if I did it the other way, if you did it like we were all millionaires implies that 2 + 2 = false. Well, we don't know. It could be true, it could be false that this was. So it might be if we're not all millionaires, and that would still work. But then you might not know. Maybe we're all millionaires secretly, and so therefore you have to be able to estimate. It only works if you know that P is false. If you know that P is false, you know the proposition is true. If the condition is true, then you have to look at Q. Because it's the key thing is the only way this can be false The only way this can be false is if the condition is only way to fail. And this is going to come up in certain other contexts, but this is a crucial sort of idea. And I go at length in here about this guarantee. And along the way, we also introduce some other notation like negation. For if P is true, then not P is false. And also for P or Q, which is one or the other. This is true if P is true or Q is true, or they're both true. And the idea here is that P implies Q. We haven't talked about logical equivalence yet, but it's going to turn out to be logical equivalent. It's always going to be true at the same time if not P or Q is true. These are actually logically equivalent. And this not P captures the bottom two rows. It says that P is false. So this is true if P is false or if Q is true. So if this actually logically captures the same, if I wrote out the truth table for this in terms of or and not, then this would be true. So this is a way to sort of understand the condition without this funny arrow here. So that's one thing. But I think the crucial then second thing is logical equivalence, which is the last sort of coming to the end of our logic ideas here. Logical equivalence of P and Q is the idea that P implies Q and Q implies P. Now, the consequence of this connection is that P guarantees the truth of Q and Q guarantees the truth of P. What this means is that P and Q, if this is true, it's claiming they always have same truth value. So, in other words, if P and Q are equivalent, if P is true, then Q is true. If P is false, then Q is false. So that's what, in some sense, logical equivalence is like, in logic, is like an equal sign with numbers. So another way to write, we can write logical equivalence as this. This sort of, the double arrow sort of suggests and Q implies P. Then another notation is sort of putting the three lines here to say these are all just three different ways of saying the same thing, but they're logically equivalent. So that's important because a lot of statements are logically equivalent, and then you can sort of anyway, that's just a really useful. I go through and talk about that in detail here. Okay, that's the last logical. This is as much sort of immediate, like this kind of low level true false kind of logic we need. The rest of this we're going to talk about later, sets and stuff like that, because we're doing with solution sets. We're doing for vectors and some geometry. Okay, and there's a little bit of sort of a orientation to proofs, because I go through a calculation here and show you that a lot of the calculations you've done solving simple linear systems are, the structure of those is like sort of an argument. Just your calculation is mimicking an argument. So you already know a little bit about proofs, but then at the end of chapter 0, there is this tutorial, and I wanted to sort of go over this in a little bit more detail because Regex asked some questions, and later on we'll ask you to write out a few proofs. So let me stop the recording and start it again.